plus so 4 kilogram mass. So this is everything that's in our system. Anything that's not the Earth or this mass is we consider to be an external agent or object external to this system. And initially we've got, this is the surface of the Earth. We've got this mass simply resting on the surface. And now an external force is applied to this mass. So somebody like me or someone who's not the Earth or something that's not the Earth or the mass is lifting this mass up from the surface of the Earth, and we're going to assume that the speed of this mass remains constant for now. So something is just coming and lifting this mass up and applying just enough force to counteract the force of gravity. So the forces are balanced, which means the mass can move up with a constant velocity. And at some later time, we've now got the mass is 5 meters above the surface. We still have the external force on it. It's got its own weight, obviously, as well. And at a later time still, its velocity is still the same. So this force just balances out its weight. And at some later time, it's now 10 meters above the surface of the Earth. Still, we've got our external force acting on it. Still, we've got the weight downwards. These two are still balanced because the speed remains the same throughout. So we've got 3 different times to look at. Here it's got initial position, or the initial position of the mass. Well, let's say, it's displacement is equals to 0. Here its displacement is equals to 5 meters. There its displacement is equals to 10 meters, if I pick a point of reference at the surface of the Earth. So the first thing we're asked to do is to figure out what is the potential energy and the kinetic energy for all of these cases. So the potential energy of the system, remember we had this argument that said because the Earth is so massive, in this case its acceleration will be negligible. If it cannot accelerate, it cannot gain kinetic energy. So the Earth does not have even the potential to gain kinetic energy from this. So the kinetic energy of the Earth remains 0, its potential energy remains 0. So all the kinetic and potential energy of the system is associated with the 4 kilogram mass. So if I want to calculate the potential energy of the system in this case, I can effectively just calculate the potential energy of the mass. Now this we know is equals to m times g times its position above the surface of the Earth. This is right that instant when we apply the force. So we're applying the force, but this mass is negligibly close to the surface of the Earth. So it's already moving upwards, but it has effectively not yet lifted off the surface of the Earth. So its y position is 0. So the potential energy initially would just be 0 because this mass is as low as it can be. The next one is pretty simple. Here, the potential energy of the mass is just its mass times gravitational acceleration times its position above the surface of the Earth. This is 4 kilograms times 9.8 meters per second squared. Now it's 5 meters above the surface of the Earth. So the potential energy of the mass in this case, if you calculate that out, you get that it is 196 joules. And for this case, where it's 10 meters above the surface of the Earth, again the same thing follows. Here its potential energy is just again its mass times its gravitational acceleration times its position above the surface of the Earth. It's 4 kgs times 9.8 meters per second squared. times 10 meters. And if you calculate this, you just get 392 joules. Now, what about the kinetic energies? We're given that this mass is lifted with a constant speed. So over here, the kinetic energy of the mass, which is equal to the kinetic energy of the system, is a half times m, whatever the speed is, squared. Here, because the speed remains constant, the kinetic energy of the mass will still be a half times m times v squared. Over here, the same thing. Because the speed does not change, the kinetic energy of this mass cannot change. So the kinetic energy is the same at all 3 points, but the potential energy is ever increasing as this mass is lifted. So we've got the potential energies, we've got the kinetic energy. The second question was, so we can see that the potential energy is changing as we lift this mass. It goes from 0 to 196 joules to 392 joules. Let's now compare this to the amount of work that is being done by this external force. So, if we were to look at the work done over here, so the work done by the external force, here we expect the external force to remain constant because the weight of our mass remains constant. So the definition of work, it's always a force, in this case the external force, dot product with a displacement. We know that the external force must just be enough to counteract the weight of this object, so it's m times g upwards, dot. Here we don't have any displacement yet, so this becomes 0 meters upwards, so we have 0 joules of work done. Right, so this just states again, if we don't have a displacement, we cannot have work done. For the second instance, so when the mass has been displaced by 5 meters, the work done by the external force, remember it's always a force dot product with the displacement. Here we've got now a force of 4 kilograms times 9.8 meters per second squared upwards, dot with our displacement, which is in this case 5 meters upwards. So I'm using j hat as just a unit vector indicating the upwards direction. We know that j dot j is just equals to 1, so what this is equals to is just 4 kilograms times 9.8 meters per second squared times 5 meters, and this is just 196 joules. Over here, doing the exact same equation, the amount of work done by the external force is equals to our external force dot our displacement. These two are again in the same direction, so the dot product just becomes this magnitude times that magnitude. So we again have 4 kilograms times 9.8 meters per second squared times now a 10 meter displacement. And this just equates to 392 joules. So we see that the work done by the external force matches at every point the increase in potential energy. So here we had no change in potential energy, or the potential energy of this mass at this point was 0. 0 work was done. In displacing this mass by 5 meters, the potential energy increased to 1.96 joules, which is just equals to the amount of work done by the external force. Here we've got that the potential energy of the mass was increased by 392 joules by being displaced 10 meters, and again we find that's equals to the work done by the external force. So what we can say, this suggests a modification to our conservation of energy statement. We can say that the work done by an external force is equals to, it seems in this case, the change in the gravitational potential energy. And we assume throughout that the speed of the mass remains constant. So if we've got a system like this, and we've got an external force doing work, but it does so just to counter some internal force, we can say the kinetic energy of the system will not change, but its potential energy will. And the potential energy change is just equals to the work done by the force. And this now is a way also to clearly show that work done constitutes a transfer of energy. So the system had no energy to begin with. We applied an external force, it lifted the mass, suddenly the system has got 392 joules of energy. So that energy was transferred into the system by the external force.